So let's start with section 6.1. Solve these examples. I'm not going to do example 1 and 2. Let's jump to the third one, which is here on this example. You will see let V be a vector space be a vector, and let W be a non-empty subset of V. That means W is a subset of V. But we need to prove that W is a subspace of V. That means here is this is theorem 6.2. Satisfy these two conditions. That's the important thing. Here is the important thing on this example, because they're gonna tell you V is all R3. W is look like this vector. A, the first component is A, the second component is 0, the third one is A. So now you need to prove the first one, A, and you need to prove B. Let's check how we're gonna work on this one. So I already know V is equal R3. So V equal R3. So now, and W is look like this, A, 0, and A. So now we're gonna take two vectors from W, exactly the same thing. If the addition give us a vector belong to this set, that means the first condition is satisfied. So I'm gonna work on the first condition. I'm gonna let U and V vectors in W. And we need to prove that U plus V is also in W. That's what we need to prove. So let U be a vector in W. So I'm going to say it's A1, 0, and A1. And V is a vector in W. So it's going to be A2, 0, and A2. You see the way, because we take two vectors from W. So it's going to be exactly the same shape of the vectors in W. The first component is A, the second one is 0, the third one is exactly the first one. That's what we did. Now we need to prove that U plus V is going to be A1, 0, and A1 plus A2, 0, and A2. The addition of these two vectors is going to be A1 plus A2, and it's going to be 0, and A1 plus A2. The result of these, check the first component, exactly the same thing the third one, which is exactly what we have the shape of W. This vector, the result vector, is in W. That means the first condition is satisfied. So U plus V is in W. The first condition satisfied. So what I'm going to do here, does condition A of the theorem hold? Yes. Now let's check the second one. Condition B. We're gonna let U is in W. U is a vector in W. We need to prove that scalar C times U is going to be in W. So U equal A, 1, 0, and A1. So if I set C as a scalar times U is going to be C, and here is the U, A1, 0, and A1. So the result is going to be CA1 and 0 and CA1. The first vector, the first element here exactly the last one. And the second one is 0. So this one, the result is a vector in W. That means the second condition, CU is satisfied. A is satisfied, B is satisfied. So in this case, we're going to say W is a subspace of V. V, which is this vector, R3. I'm not talking about this vector V. No, I'm talking about V as an R3, which is equal R3. So in this case, the second condition is satisfied, and we're going to say W is a subspace. That's what we need to do almost on all these examples. Let's check that. So now look to example 4. It's exactly the same thing. But again, we need to focus on how it's look like W. So this is the same theorem, 6.2. We need to prove that W is a subspace from the V. Look how it's look like W. W equal A, negative A, and 7A. So now we need to prove that W is a subspace. That means we need to satisfy these two conditions, A and B. So let's assume that we have V equal R3 and W, the shape of W is, the vector is going to be A and negative A and 7A. That means the shape of the vector W, the first element is A, the second one is going to be negative A, the third one is going to be 7A. So let's satisfy the first condition. A, we're going to let two vectors belong to W. So I'm going to let U and V vectors in W. Then U plus V. First of all, we need to write down the vector U, how it's look like. U equal, I'm going to say A1 and negative A1 and 7A1. And the vector V is going to be, it's A2, negative A2, and 7A2. So you see these two vectors R and W, so it's going to be look like the vector W, which is the first element. The second element is going to be negative. The third one is going to be 7 times A. Now we need to prove that U plus V equal, the result is going to be in W. So here is A1, negative A1, and 7A1, plus A2, negative A2, and 7A2 is going to be equal. A1 plus A2, the result when you add these two vectors is going to be A1 plus A2. Then negative A1 minus A2. And 7A1 plus 7A2. Then I can simplify these by, here is A1 plus A2. This is the first element in this vector. The second element, if I took the negative sign as a common, so it's going to be negative A1 plus A2, which is negative the first element. The third one, if I took 7 as a common, is going to be A1 plus A2. So now the result is exactly like a vector in W. The first element is A1 plus A2. The second one is negative the first element. The third one is 7 times the first element. So exactly the same thing here. That means the result here is a vector in W. So U plus V is in W. That means the first condition is satisfied. Now we need to check the second one. Condition B from the theorem, let C is scalar. So C times U is going to be C times the vector U, which is A1, negative A1, and 7A1. And it's going to be equal CA1, negative CA1, and 7C, and here is A1. Again, it's exactly like the vectors in W, because here is CA1, the first element. The second one is going to be negative the first element. The third one is going to be 7C, the first element, which is 7CA1. That means the result is in W. So CU is in W. That means W is a subspace. That's it for this example. So in this case, the second condition satisfied. This one, yes. This one, yes. And W is a subspace. That's it for this example. Let's check. Here we go. So example 5, again, we have to focus on how it looks like W. So we have V equal R cubed, and W is, we have A, B, and the absolute value of A. So let's check the first condition. First of all, we're going to let two vectors belong to W. So I'm going to let U equal A1, B1, and let's say the absolute value of A1. And the vector V is A2, B2, and the absolute value of B2, of A2. So these two vectors are in W. So now we need to prove that U plus V equal A1, B1, and the absolute value of A1. We're going to say plus A2, B2, and the absolute value of A2. This one is going to be equal A1 plus A2 and B1 plus B2. And the third element is going to be the absolute value of A1 plus the absolute value of A2. The first element, exactly what we have here. The second element, exactly what we have here. But the third element, the absolute value of A1 plus the absolute value of A2, we can't say it's equal to the absolute value. That means the absolute value of A1 plus the absolute value of A2 is not equal to A1 plus A2. That means even if you check numbers, like negative number here, both is going to be positive. So like -1, -1, the result is going to be 2. If you take -3 here and 1 here, that means it's going to be 3 plus 1, 4. But if you say -3 plus 1 is going to be -2. Absolute value of -2 is going to be 2, which is these two values are not equal. That's why this one is not exactly like the vectors in W. So in this case, this is not in W. So U plus V is not in W. So the first condition is not satisfied. So we can say no. Let's check the second condition, is satisfied or no. But in this case, if you just prove that the first condition is not satisfied, that means W is not a subspace. But here they ask you to prove that the second condition also. So let's prove the second condition, which is C times U is going to be equal C times U, which is A1, B1, and the absolute value of A1. So in this case, this one is going to be equal CA1 and CB1, and here is going to be C, the absolute value of A1. Let's check this one is satisfied. This one is NW. The first element, yes. The second element, yes. But the third one, if you have CA1 equal to CA1, these are not equal. If you took C as a negative number, like if you set C less than 0, negative number. So -1, for example, times any number is going to be negative. But if you multiply the negative number times any number here and take the absolute value, the result is going to be positive. That means this one is not equal to this one. That's why the result is not in W. So CU is not in W. In this case, W is not subspace. That's it for this example. So this one is not, W is not a subspace. That's it for this example. Let's check example 6, if we can satisfy these two conditions. So they're telling you V is all the matrices with n times n prime. V is all the matrices with m, and they're telling you W is A, like a matrix in V, A, and M, okay, such that the determinant of this matrix of matrix A equal 1. So here is the condition. Now let's see how we're gonna check if A is a matrix, is a W is a subspace or no. So let's work on the first condition. If you check, how are we gonna assume that two matrices A, that means the determinant for these two matrices in W equal 1. So if you let, I'm talking about the first condition, let U is a matrix with 1, 0, 0, 1. If you look to this matrix is belong to the W, and the determinant for this matrix 1 times 1 minus 0. So determinant equal 1. So the determinant of the matrix U equal 1. So that means U belong to W. Let V the matrix V equal, we can say the same thing, 1, 0, 0, 1. Determinant for matrix V is going to be equal 1. Now we need to satisfy the first condition. If U plus V is going to be equal, the matrix 1, 0, 0, 1 plus the matrix 1, 0, 0, 1. If you add these together, the result is going to be 2, 0, 0, 2. The determinant for the new matrix is going to be 4. Determinant for this matrix is going to be 4, and this one is not equal 1. That means U plus V is not belong to W. U plus V is not in W. So the first condition is not satisfied. So we're just going to choose no. Let's check the second one. The second condition, C times U, C is a scalar, is going to be C times the matrix 1, 0, 0, 1. And this one equal C, 0, 0, and C. The determinant for this one is C squared. Determinant for this matrix is going to be C squared. So now C is any number. So if you choose one, yes, it's going to work. But what about other numbers? -2, -4, -6, 7, 8, 10. That means not always the determinant for this matrix belongs to W. So in this case, because C is any number, that means CU is not in W. In this case, W is not subspace. That's it for this example. So we're going to choose no here, and it's not a vector of phi or subspace. That's it for this example. So example 7, here's the two conditions, and they ask you V is matrix with n times n, and W the matrix, any matrix A belong to V with this condition. Be careful, they're telling you where B is a given fixed matrix, so you don't have to change B. B is a fixed matrix. That means in this case, A equal A, because B is a fixed matrix. So we already know V equal all matrices with n prime, and they're telling you W equal matrix in V with this condition, AB equal BA. So first of all, in this example, you're not going to assume that a matrix. Try to work smarter than that. Like, you're not going to assume that matrix with element A, B, C is going to be a little bit harder. So let's think in another way. We're going to assume that two matrices belong to W. So we're going to let the matrix A and C are in W. Let's work on the first condition. If I say A plus C, A plus C, B is a fixed matrix. B is a fixed matrix. So if I said that this one is exactly like, I need to satisfy this condition. So here is A plus C times the fixed matrix B times the fixed matrix B. Now I need to simplify this one, work on this one to get the second part here. So in this case, this one is equal A B plus C B. And then AB equal BA and CB equal BC. So and this one is going to be equal BA plus BC. That means this one equal B and here is A plus C. That means we satisfy these conditions here. Any two matrices, the addition of these two matrices with this condition is going to be equal B times the matrix A plus C. So that's mean A plus C is in W. This is the first condition. The second condition, let C is a scalar. Then C times the matrix A is going to be equal. Now I'm going to go to this condition, which is the matrix B. That means it's C times A with the matrix B. So in this case, this one is exactly the same thing, C, and here's A with the B. If you see the properties of matrices, that's what we're doing here. Now, here is the C as a scalar. A times B is equal B with the A. That means this one equal C with the B, and here is the matrix A. So in this case, it's going to be B times C times the matrix A. So we start from this part with the first condition, C times the matrix A times the fixed matrix equal B and C times A. That means CA is in W. So W is a subspace of V. So we're gonna say this is yes, and it's W is a subspace of V. That's it for example 7. So for example 8, again, V equal polynomials with the second degree, and W, that's how it look like for W. So now we're gonna let U and V exactly like two vectors or two polynomials from W. So the first condition, we're gonna let U equal, the first polynomial is going to be, I'm gonna say B1x plus C1x squared. And I'm gonna let V equal B2x plus C2x squared. Now I need to find U plus V belong to W. So it's going to be B1x plus C1x squared and plus B2x plus C2x squared. Now add these together, combine the like terms. So it's going to be B1 plus B2x plus C1 plus C2 x squared. This is a number with a coefficient with the x, and here's another coefficient with x squared. That mean is exactly like any vector in W, coefficient with the x, coefficient with the x squared. So this one is in W. So in this case, the first condition is satisfied. Let's work on the second condition. If you say C times U is going to be C as a scalar, and U is B1x plus C1x squared. So the result is going to be CB1x plus CC1x squared. Now let's look this vector. A number with the x plus a number with x squared. Because a scalar times the coefficient is still a scalar and it belongs to W. So this one is in W. That means W is a subspace of capital V. So here we just prove that the first condition satisfied, the second condition satisfied, and this one is a subspace. That's it for example 8. So if you look to example 9, it's exactly the same thing, but we have condition. It's like example 8, but let's check the condition we have. We have the vector V, which is all polynomials with degree 2, and we have W equal. They're telling you it's A plus BX plus CX squared. A plus BX plus CX squared with the condition that means the coefficient A, B, C is equal 0. So let's check that. The multiplication of these two conditions is supposed to be equal 0. So first of all, we're gonna let U, the first condition, we're gonna let U equal A1 plus B1x plus C1x squared. And we're gonna let V equal A2 plus B2x plus C2x squared. So here is U and here is V. Now U plus V is going to be equal A1 plus B1x plus C1x squared and everything plus A2 plus B2x plus C2x squared. We can combine these two polynomials by adding the like, combining the like terms. So this one is going to be A1 plus A2 with just as a constant plus B1 plus B2 with the x plus C1 plus C2 with x squared. So now that's U plus V, but we need to check, is this condition equals 0? That means the first element times the second one times the third one equals 0. You can't say that this is equal 0. So that means A plus A1, A1 plus A2 times B1 plus B2 times C1 plus C2 is not equal to the 0. So in this case, u plus v is not in W. Let's go to the second condition. The second condition, you're going to say C times the matrix U, which is equal C times A plus A1 plus B1x plus C1x squared, which is equal C times A1 plus C times B1x plus C times C1x squared. And in this case, the same condition. You can't say C1A1 times C1 CB1 times CC1 equal 0. This is not equal to the 0. So again, CU is not in W. So W is not a subspace. That's it for this example. We're just going to say that this is not satisfied. The second one is also not, and it's not a subspace. Let's see the second condition. Because the second condition, we can say that it's equal 0. This is equal 0. That means CU is in W. Because A1 times B1 times C1 equals 0. So if you multiply the scalar, one of these elements is going to be 0. The result equals 0. So the second condition is satisfied. But it's still W is not a subspace because the first condition is not satisfied. So this one, yes, the second condition is satisfied, but W still not a subspace. Yep, we got it right. So let's satisfy the two conditions for this example. So we're gonna let two functions belong to W, like f and g. F and g are in W. So that means f plus g is going to be equal f to the negative x plus g to the negative x, because that's how it looks like our function. So this is addition of two functions. So it's going to be f plus g to the negative x. That means this one is going to be equal negative f plus g to the x. So f plus g is going to be negative f plus g to the x. That means f plus g is in W. The second condition, c times f to the negative x is going to be, I can take the c out, c f to the negative x, which is equal negative c f to the x. And this one equal negative c, you can keep the negative out, is going to be negative, and c with the f to the x. That means cf to the negative x is going to be negative cf to the x. This is a function with the scalar. This is the input X. So CF is in W. That means W is a subspace of capital F of V. So the first one, yes. The second condition also yes. And then it's a subspace. That's it for example 10. So example 11, we have three matrices. They ask you to find A times the matrix A plus B times the matrix B. A and B are scalars. So that's what they ask you to find first. A times the matrix A plus B times the matrix B, which is equal A times the matrix A 1, 1, negative 1, 1, plus the scalar B times the matrix B, which is 1, negative 1, 1, 0. So the result is going to be A plus B, and it's going to be A minus B, and it's going to be negative A plus B, and here is going to be just A. So that's it. This is the first thing they ask you here. So you're going to type here A plus B, and you're going to type here A minus B, and we're going to type here negative A plus B. You're going to say B minus A, and here is going to be just A. Now they ask you, is C span AB or not? Span, that's mean. Can you write down C as a linear combination of the matrix A and B? So when I ask you C span the matrix A and B, it's mean, can I find the scalar that means C? The matrix C is C1 with the matrix A plus C2 with the matrix B. Let's check that. So the matrix C is 1, 2, 3, 3. Equal, I'm going to say C1 with the matrix A, 1, 1, negative 1, 1, plus C2 with the matrix B, which is 1, negative 1, 1, 0. So it's going to be 1 equal C1 plus C2. 2 equal C1 minus C2. 3 equal negative C1 plus C2. And the 3 equals C1. So now we need to find C1 and C2. You already know how that means C1 equal 3 from the third one. If you plug in this one here to get C2, so we're going to get a 3 equal negative 3 plus C2. Now in this case, C2 is going to be equal 6. So I have C1 and I have C2, but let's check. This C1 and C2 satisfy the first and the second equations. So if I plug in here, it's 2 equal. C1 is the 3 minus C2 is 6. 2 is going to be equal to -3, and this is contradiction. That means even if you check the first one, it's going to be contradiction. That means this C1 and C2 is not satisfy these all equations here. In this case, C, the matrix C can't span the matrix A and B. Because we found C1 and C2, but does not satisfy all these equations here, which we got contradiction. So that's what you're gonna type here is not span. That's it for this example. P of x 1 minus 2x, Q of x equal x minus x squared, and we have R of x equal -2 plus 3x plus x squared. Then S of x is 5 plus x squared. Now we need to prove that S of x is span to the P of x, Q of x, and R of x. So that means there is a scalar C1, C2, and C3. So I'm going to write down S of x, which is 5 plus x squared equal C1 times P of x, which is 1 minus 2x, plus C2 times the Q of x, which is x minus x squared, plus C3 times R of x, which is -2 plus 3x plus x cubed. X squared. Let's simplify by distributing C1 and C2 and C3. So 5 plus x squared is going to be equal C1 minus 2 C1x plus C2x minus C2x squared plus C3 -2C3x -2C3. So minus here 2C3 plus 3C3x plus C3x squared. Now we're just going to combine the terms, the constant with the terms, the coefficient with the x and the coefficient with the x squared. So this one, just a constant by itself, and this one is a constant by itself. So it's going to be C1 minus 2C3 plus, with the x, we have these two, and we have this one. So with the x is going to be -2C1 and plus C2 and plus 3C3. With the x squared, we have these two terms. So -2C2, -C2, and plus C3. This is with x squared. Now we're just gonna, we have equal sign. That means 5 is going to be equal C1 minus C3. And the second one, we have 1 equal -2C1 plus C2 plus 3C3. And we have the last one also 1 equal -C2 plus C3. Now we need to solve this system to find C1, C2, and C3. So I'm going to solve the first one. C1 is going to be equal 5 plus 2C3. And I'm going to solve this one because it's easier to solve. I'm going to say C2 equal, move this one to this side, so it's going to be positive. It's going to be C3 minus 1. Now I'm going to plug in these two here on the second one. So the result is going to be 1 equal negative 2 C1, which is 5 plus 2 C3, plus C2, which is C3 minus 1, plus 3 C3. These two sides are equal. If we solve this one, we have to find the value of C3. So 1 equal negative 10 plus minus 4 C3 plus C3 minus 1 plus 3 C3. If you look here, this one, and this one, 1 plus 3, 4. 4 cancel with this one. The left is 1 equal negative 11, which is contradiction. We couldn't find the value of C3. In this case, S of X is not span of P of X, Q of X, and R of X. That's it for this example. So we're just gonna say it's not span. Did I choose? Okay, that's it. So example 13 is the matrix with 2 times 2 spanned by these 3 vectors. So I'm going to say this is V1 equal the first vector, V2, and here's V3, and V4 is going to be 0, negative 1, 1, 0. So we need to find the span. That means any matrix with dimension 2 times 2. So I'm going to say E11, E12, this is our matrix, E21, and E22 equal C1 with the first vector V1, which is 1, 0, 1, 0, plus C2 with the second vector 1, 1, 1, 0, plus C3 with 1, 1, 1, 1, V3 plus C4 with 0, negative 1, 1, 0. Now let's find the scalar. So in this case, E11 is going to be equal C1 plus C2 plus C3. C4 is going to be 0. C1 plus C2 plus C3. And E12 is going to be equal 0, C2, C3, negative C4. C2 plus C3 minus C4. And E21 is going to be equal C1 plus C2 plus C3 plus C4. And E22 is going to be equal just C3 because 0, 0, and 1, and here's 0. That means all the matrices with this coefficient, so all matrices with 2 times 2 is going to be equal span with V1 and V2 and V3 and V4. Why? Because it's a subset of the matrix E11, E12, E21, and E22. That's it for this example. So it's just a proof that this is a span So you can say yes. That's it for example 13. That's it for section 6.1.